Convective systems can, in addition to generating strong winds, hail, and produce large amounts of rainfall. Convective systems that yield significant rainfall require somewhat specific humid conditions. Typically, convective storms are spawned with humid regions because it is the moisture in the form of water vapor that provides both the source material for precipitation and an important fraction of the energy that drives the convection. The large-scale features of the atmosphere are crucial for providing the general environment in which rainstorms form. The abundance of the atmospheric moisture, both the material source of the rain itself and the energy basis for vigorous convection. Moisture is often advanced great distance by the synoptic scale motions into a region where it may be forced to rise with vertical wind currents and that are driven by mesoscale pressure gradients and low-level convergence of the air. Look at this table. This is work from Fan Limiao, who, based on the rainfall data from more than 2,000 national weather stations and part of the sounding data during 2002 to 2011, almost 10 years. The following parameters, including the height of 0 degree, the height of 20 below 0 degree, the level of free convection, the surface temperature and the dew point, the temperature difference between 700 millibar and 500 millibar, the temperature difference between 850 millibar and 500 millibar, the vertical wind shear of 0 to 6 kilometers, the dew point at 1.5 kilometer, and the difference between temperature and the dew point at 1.5 kilometers. These parameters are used to effectively distinguish the environmental background of the four types of severe convective weather. Differences of the environmental background are relatively significant between the heavy rain and the large hail and the severe convective winds. Comparing with the latter, the heavy rain has smaller temperature differences between 700 millibar and 500 millibar. The smaller temperature difference between 850 millibar and 500 millibar, with vertical wind shear of 0 to 6 kilometers, relatively high height of 0 degree and the height of 20 below 0 degree, large dew point temperatures on the surface and on the 1.5 kilometer height. We use the equation to describe the many factors that can lead to heavy rainfall. Equation P relates to rainfall rate and duration. Rainfall rate is respect to precipitation efficiency, ascent rate, and water vapor mixture ratio. Hail and convective windstorm largely depend on subsynoptic scale and mesoscale forcing, which are closely related to atmospheric dynamic process, and the model can be well captured mostly a dry process. Short-time heavy precipitation requires that both external forcing and convective processes can be correctly simulated. The description of physical processes is important. In addition, short-time heavy precipitation can occur without obvious external forcing, small-scale rainstorm. Therefore, the uncertainty of model forecast is much higher. It is important for model users to know that, in general, all numeric weather prediction models are least skilled at forecasting precipitation, although most high-resolution models are better than large-scale models because they can run sophisticated schemes that directly predict precipitation and clouds. They also account for internal cloud processes. As for short-time heavy rainfall, a systematic, comprehensive analysis forecast process includes synoptic and mesoscale analysis to help us have awareness on expected weather. Then, after checking the current conditions at the surface and aloft, and then comparing them to the model forecast initial conditions or the 0-hour forecasts, we decided that they are close enough to allow us to trust that the models are at least starting off well. After analyzing the model mesoscale analysis and sounding analysis of favorable environment conditions, the high depths of high moisture or the trend of moisture advection for heavy rain. We also pay more attention to the precipitation mode, the moving speed of reflectivity or rain cluster. In order to recognize the precipitation mode, there is a case to help you have an idea of the precipitation mode. The model forecast of the 3 hours precipitation at the initial time of 20 o'clock on 28. In the first line, the second line is the model forecast the 3 hours precipitation at the initial time of 8 o'clock CST on 29. The third line is the model forecast that 3 hours precipitation at the initial time of 20 o'clock CST on 29. Through the numeric forecast of different initial times, we can see that the precipitation mode is cluster and it's located stably in there, which will get your intense attention. Pay attention here, please. We have known that in general all numeric weather prediction models are at least skilled at forecasting precipitation. So firstly, the model must predict the process. Relatively speaking, look at this image. The elongate mode is the fast-moving rain masses, and the cluster in the right, the clusters are slow-moving masses. The precipitation distribution is significantly elongated along the movement direction of the system, indicates that the precipitation system is moving fast. This is the intense rainfall which happened at urban area in Shanghai from 18 o'clock to 19 o'clock on July 22, 2015. The accurate precipitation in 1 hour, especially at 18 o'clock to 19 o'clock, is more than 20 millimeters. This time is back in home time, in which people will obviously consider the weather situation. These two images are Shanghai Meteorological Service 9 kilometers model forecast at the initial time of 20 o'clock CST on July 21. In the left, it is 6 hours total precipitation from 8 to 14. In the right, it is 6 hours total precipitation from 14 to 20. In comparison of real situation, the time is false, which is earlier than the real rain time, and the location is west of the actual position. The below three images are the 1 hour accumulated precipitation of 3 kilometer models. In comparison of 9 kilometer model forecast, we can see 3 kilometer model, the time and the location is better than 9 kilometer model forecast. But it's not precise. Then is there any useful information we can get? Obviously, the precipitation mode of both models forecasts are cluster mode, and the speed of the rain cluster stays there stably. So we can have the awareness that the high possibility of heavy rain. This is the case in Guangzhou. Very extreme rainfall event occurred in the center of Guangzhou province on May 7, 2017 in the Zhengcheng and Huadu district of Guangzhou within maximum 1 hour precipitation exceeding 180 mm and 3 hour rainfall exceeding 330 mm, causing severe economic damages. Look at the real observations. The left image is 3 hours precipitation in surface station from 2 to 5 o'clock. The middle image is 3 hours precipitation in surface station from 5 to 8 o'clock. The right image is 3 hours precipitation in surface station from 8 to 11 o'clock. We can see the rain cluster moves slowly from the east to the west. These images are the 3-kilometer resolution model in Shanghai, which started from 23 o'clock May 6. Left image is 3 hours precipitation from 2 to 5 o'clock CST, May 7. The middle image is 3 hour precipitation from 5 to 8. The right image is 3 hours precipitation from 8 to 11. The model forecast indicated that there was no significant precipitation in 5 to 8 3 hours. These are also the 3-kilometer resolution model in Shanghai, but started from 2 o'clock CST, May 7. The left image is 3 hours precipitation from 2 to 5 o'clock. The middle image is 3 hours precipitation from 5 to 8. The right is 3 hours precipitation from 8 to 11. The model forecast indicates that there was significant precipitation in 5 to 8 3 hours. So the two starting time model forecast was so different. Which one was accurate? So we need real observations. These are issues of rainstorm warning signals in Guangzhou at 2 o'clock in the morning. We see that heavy rain observed in the stations. So combined with high resolution numeric prediction, which starting from 2 o'clock CST, may be delivered to the forecast delayed in 1 hour. At 3 o'clock, we can have confidence that the high possibility of heavy rainfall will happen in Guangzhou. On the basis of the analysis of real-time observations and the continuous tracking of the model forecast trend, we have the confidence of high possibility of heavy rain in the middle of Guangdong. There are 1-kilometer resolution model products in south of China, which starting from 2 o'clock to 4 o'clock CST. This line model products are starting from 2 o'clock CST. The second line model products are starting from 3 o'clock. The third line model products are starting from 4 o'clock. The trend of the model forecasting in different starting time indicated backbuilding of the rain cluster and moving slowly, which indicated high possibility of rainfall at the red solid circle area. In summary, for heavy rain, a systematic comprehensive analysis forecast process including synoptic and mesoscale analysis to help us have awareness on expected weather. They are checking the current conditions at the surface and aloft, and then compare them to the model forecast initial conditions of the 0-hour forecast. We decided that they are close enough to allow us to trust that the models are at least starting off well. After analyzing and the model mesoscale analysis and sounding analysis of variable environmental conditions, moisture, or the trend of moisture advection for heavy rain. We also pay more attention to the precipitation mode, moving speed of rain cluster. It is important for model users to know that in general, all numeric weather prediction models are least skilled at forecasting precipitation, but with the developing of technology, we can use multi-high-resolution model integration to get the best forecast in heavy rain.